Okay, everybody's cool? All right. So where was I? All right, okay. So we Fluence is the compute. So if you look on the right, you have a peer-to-peer network, a stylized peer-to-peer network, and the green round things are clients, could be a browser, and then you have some nodes in that network. One's called a relay, just for make sure a relay is a node that's publicly accessible. It could be in front of other nodes or peers that are not publicly accessible because of NAT reasons or whatever. And then we actually can deploy services onto these peers. Now, services are actually WebAssembly interface WASI modules. And that's where you get a lot of portability and openness in your service development, where the service is your business logic. So, and you can extend the reach of your peer-to-peer compute by writing adapters in those WebAssembly modules to actually reach out to existing resources like IPFS, microservices you already have in place, and whatever APIs you already have. So you don't have to like port everything. You can actually use what you have and then build forward to start building up your decentralized footprint. So let me give you an example. Let's just say we have a browser and we have a chat application, or we want to send some text. So we want to send, hang on, text from here to here. And our text is, I don't know, :+1 pair to peer. So basically, I thumbs up peer to peer, but we misspelled the first peer. We call it pair. And now we have two services, a spell check service. I don't know, let's just call it this one, and a emoji PNG injection service, which is here. So now what we need to do is we need to get this client, which is a browser. So a browser can't have a full connection to the network just by, the short-lived connectivity you get from a browser, HTTP, to the relay. So we have to use the relay. We get to the relay. We have our text. We would go to the spell check service. So this is a really good spell check service. It actually knows that it should be peer-to-peer, not pair-to-peer, or at least peer-to-peer, however you want to fix it. But we have that state change now in our text, and then we move on to the next service, which now interprets the :+1 as a thumbs up PNG, injects it, and then we end up delivering this to whoever you are at that other client, which actually, if it's a browser, also should be through a relay, but that service actually could be on a relay node. So I told you before that we didn't want to have these services available through traditional DNS reliances. So there is no REST endpoints. There is no JSON RPC. So in Fluence, so how do you address this? And this is where function addressability comes in, as I alluded to earlier. So basically, a service has a unique one or more WebAssembly modules, which you currently need to write in Rust, and you address them by their unique service ID, which you get when you deploy a service to a peer, and the peer ID. So it's not dissimilar to the content addressability model you see in IPFS, for example, with the CID, where you take the hash of the document and then the multi-address of the node that hosts it. So if you want to be really nitty-gritty, the unique service ID is fundamentally an identifier created from a UUID4. So it's unique, and it's mapped against a blueprint ID. And the blueprint ID is actually the sequential hashes of the various modules making up your service. So this brings you certain guarantees in terms of versioning and all this stuff, because once you have your blueprint ID, you know what you're running, and you change the code, you change the service, you have a different blueprint ID, just like you have with the document hash. So so obviously you need a tool to be able to address it, right? You can't just type into the browser the peer ID, which literally is just the hash of the public key of your peer, and service ID. So what we created a language. It's a peer-to-peer programming language called Aqua. And Aqua actually lets you compose these distributed services into decentralized applications. And what happens essentially on every peer, and we go through this in the next few slides, on every peer you have an AVM. It's an Aqua virtual machine which executes the compiled Aqua, and it's on every peer, and that helps you locate if the service you want is on that particular peer, or if you have to use discovery in the network to find the peer that hosts the service. So that's where the addressability comes in. The WebAssembly modules themselves actually are executed on what we call the Marine runtime, which is a general purpose WASI runtime built on top of Wasmer, and that's also available in every of those full node peers. Okay, so if you look at it, how Aqua then and Marine work together, you basically have these peers. On each peer, you have the AVMs. You compile Aqua to an intermediary representation called AIR, Aqua intermediate representation, and you can think of it as bytecode, even though it compiles into something that looks much closer to Lisp closure. And you can think of the Aqua virtual machine. I mean, it's a virtual machine. It's a WebAssembly module in itself as a stepper that steps through the unprocessed pieces of the AIR script left. And Marine basically then, when called upon, runs these WebAssembly modules, and those WebAssembly modules actually are share nothing, but they expose interfaces and functions that you can specify, so you can actually link them with a configuration file which makes the service. So you could actually use different combinations of modules to create different service types, blueprint types, and really facilitate the reuse of WebAssembly through those modules. Now, okay, one more thing. There is this. So at this point, between the previous diagram and this diagram, and look at those green little dots, you probably deduce that the data, the request response model is a push model. It's not your traditional client server model where you have the client, you get the spell check done, you get the result back. Now you call the emoji service, you get the result back, and then you send it to the client. What actually happens is we have this push model. So unless you specify specifically to report back to the client, it literally, like what we call a particle, it's a smart package. It goes out to the network and then travels on the network without ever having to go back to your client, which actually allows you to create very, very thin clients. And the core concept behind that capability is what we call a particle. And particles are conflict-free replication data structures, and they combine data. So in this case, it was our text I colon plus one peer to peer. That's our data. Then the execution sequence, which is basically Aqua, and we'll go through it, but that basically specified go to the node where the spell check is, do whatever you need to do, then go to the node or the peer where the emoji injector is, and then deliver it to wherever your endpoint was. So when you connect to the network from a quote unquote client, you need this lib P2P connection. Everything is built on lib P2P, by the way. This is our substrate, and you have to connect through that. So it's not REST or JSON RPC, it's lib P2P that gives you the connectivity even at the client. And you can do this. We have this for browser. We have it through TypeScript. You can have a bigger node app, or you can use it Rust for that. And those particles, it's really, really cool actually in it by itself, because Aqua not only allows you the sequential but actual parallel processing. And that actually allows you an enormous flexibility and a very high level of abstraction between the lib P2P substrate and your programming interface into that compute model. So just quickly, what we have on tooling, we have a Rust SDK actually called Marine SDK. There's two of them, and basically what that allows you to do is to wrap Rust to help you write effective WebAssembly, compile to effective WebAssembly, WASI targets, and also to really give you testing around WebAssembly modules. Now, a side note on Rust. I said you need Rust right now. It's the only way. You can do it in C, C++, but the only way we support right now out of the box through SDKs is Rust to write WebAssembly modules. And some people get really nervous because Rust can be challenging. However, in this WebAssembly module, the level of Rust you require is literally the first 4 chapters for the following reason. WebAssembly is pass by value only, so you don't have any of those reference issues, the time issues, none of this. It's very specific types, and it's a very restricted type set. So there are no generics, no generic traits, no trait objects, nothing. And WebAssembly module is single threaded, so you're not looking at async or concurrency. So really, the subset of Rust required to produce high quality WebAssembly modules literally is not much different than how you would write it in JavaScript or Python. So if don't be afraid of it's Rust is complicated, steep learning curve. The part of Rust you need in order to be successful writing WebAssembly modules, if you have any programming experience, is not particularly steep because it eliminates everything that makes Rust really, really cool. And you still get speed. So the second part of the SDK is also very, very cool. And it really pertains to how you test. In general, when you do a unit integration test, you use the code you write to test. So you write your test against that code. And that's cool. But our output aren't your ordinary binaries. They're WebAssembly modules that actually share nothing. So when you want to do integration tests, how do you test those modules in a testing environment as opposed to having to deploy them and then manually write some smoke test? That's super inefficient. So what we created is we have created a test overlay that runs just in Rust, your environment, your package manager, and all the testing is cargo. So if you do tests, it's called cargo test, and then some flags, and you can use that. But what we do is you first compile everything to WebAssembly, and then we have a testing wrapper that actually tests against the actual WebAssembly modules, not your Rust code, and that actually allows you to test as if you were testing the modules on the deployed on the network. And that is actually super, super cool in it by itself because it really helps you. So, and we all have other things like VS Code, early markup capabilities, prompts, and all that. And we're working to make this better and better and better from an experience. So, as part of hackathon, by the way, if you have any comments, any requests, whatever, in terms of features, or want to say something about the tooling, please do not hold back. We also have Fluence Js. So Fluence Js is an interesting beast, if you will. The origins of Fluence Js is really to bring Fluence compute and peer-to-peer connectivity to the browser. And so that comes out of Fluence Js, but you can now also use it as a node application. And we have the Aqua virtual machine running inside that Fluence node, Fluence JS. So we actually can expose interfaces and run them through Aqua as if they were WebAssembly services out on the network. The downside of Fluence JS right now is that if the logic you write inside in JavaScript is not easily redeployable as you would if you had a WebAssembly module. So if you wanted to scale your service, you wanted something like you want to run it in parallel like 10 times, you would have to deploy your own node 10 times instead of using other nodes. Now, we are having Marine, it's in progress. I don't want you to think about it for the purpose of the hackathon, but for information purposes, it's coming to Fluence JS. So you can eventually run WebAssembly modules on that node, that TypeScript node, as if it was a Rust node. However, we believe Fluence JS, there's a lot of reasons why you want it, and I'll get into this a little bit. But compared to Rust, it will never be as performant and robust in terms of type checking, all the stuff that you get from Rust nodes. But there are really good use cases for it. And of course, one really good use case is the Node app as a pure client in it by itself. Get into this in a little bit. And then, of course, there's Aqua. So I keep talking about Aqua, and eventually we're going to get into Aqua. But it's a high-level language. It's a compiler. which compiles that high-level language into immediate representation, and then we have a CLI around it. And the CLI not only lets you compile, but it also has a convenience function or syntactic sugar that lets you deploy what you compile onto the network. It lets you run Aqua and a whole bunch of other features, which are currently all in the Aqua CLI tool. Now, Aqua, finally we're going somewhere. If you have any questions at this point, anybody has any question at this point? All right. So let's just dive right in. So, well, actually, before we dive right in, let me jog your imagination. We have a service out there. We wrote it in Rust. It's WebAssembly into a WebAssembly module, and we call the service a greeting service. That greeting service has one function called greeting, and it takes two parameters, a string and a Boolean. So the string basically is a name, and the Boolean determines what the greeting type is. So if basically if I call this greeting function on this WebAssembly service with Paris P2P, and the Boolean is true, then it would say, hi, Paris P2P, which is a really good thing to do on this wonderful Friday afternoon. If the Boolean was false, then it would actually say, bye, Paris P2P, which we reserve for Sunday evening, right? So for the next few days, we got to have it true, and then on Sunday, we go to false. And we basically recreate this binding, this interface in Aqua. So because it's just like if you have worked on Solidity, for example, with the ABI, eventually we're going to create a binding to what the service that's deployed on the network. So let's have a look at the implementation of the Aqua greeting function. So it takes this name, which we said was Paris P2P. We take this Boolean, which could be true. And now we have additional parameters in that function signature. One is the node, which is actually the peer ID that hosts the deployed service. And then we have the greeting service ID is also a string, which actually is the unique service ID of that service. So we could have this service like 50 times in the network, and we were going to call this unique one. So if we wanted to parallelize it 50 times, we had 50 function addresses or function addressability tuples, and we could run this 50 times in parallel. So now the really cool stuff comes. So you're on a client, could be a browser, right? And now in Aqua, you specify on node. So on this particular peer ID that hosts that service, you want to create this binding for this interface to this particular service ID. And then you call within that namespace that greeting function with the actual parameters, Paris peer-to-peer, and I think we said true. And then you get a result back. Now, if you ever program peer-to-peer applications at the libp2p level, you are totally friggin' impressed right now. However, if you're not, let me explain to you why this is really, really cool. And it's really, really cool is because you don't have to do anything about discovery, topology, hop management, nothing. And if you look in the upper right corner, so we have this client here, right, that basically bundles up this particle we talked about before, and sort of flings it onto this relay node right here. And then it sorts out. You don't have to do anything. You don't have to specify, I want to be on a relay node. This is Aqua takes care of that for you. Whatever is the closest, most efficient relay, it connects to that. And then it figures out, okay, we don't have that service on that relay node, on that peer. Now it finds and routes that particle, that smart package, to the destination peer, that hosts that service. Then on that destination peer, on Marine, that it executes that WebAssembly module now, and we get that state change, right? We get this this new string back, and then without you having to do anything, it actually routes it back, in this case, to the client. So if you think about this, like if you didn't have Aqua and you just had a bunch of multi-addresses, you very easily see, even if you do it in something that doesn't require a lot of code like Python, which actually is a real shitty P2P implementation, you very quickly realize that this is like a lot of boilerplate to keep routing this. And this is where Aqua comes really, really, it's super ergonomic. And sort of as a side point, we actually use Aqua not just to call these to compose services into peer-to-peer applications, but we actually use it to program the network itself, which hopefully we'll have time is actually also super, super cool, super efficient on how to deal and program peer-to-peer networks themselves. So what Fluence Compute works, it works today, but it's not complete. And so Marine on the browser, Wasm on the browser, we started it. It's proof of concept, and for a limited subset of WebAssembly type modules, it's available today. Don't worry about it for the hackathon. We are working. We have almost completed. Actually, today it should be ready. Registry, which is a managed service and protocol discovery. So it actually all the specification of the node and the service ID I just showed you, you can all automate that and basically use hash representations of those key values. We have Trust Graph. It's basically a web of trust for P2P nodes and hosted services. If you go back to early on, I said the Fluence network is open and permissionless, which is great, but it opens up some pretty significant gaps. And Trust Graph is one tool that helps you manage those security, those trust gaps. Because just to make sure, the Fluence peer-to-peer network, I mean, it's open. It's not owned by Fluence. We call it Fluence peer-to-peer network, but whoever joins is part of the network. And it's truly a peer-to-peer network. The compute is not running like it was on chain. So in the blockchain, every time you add another node, you improve your security, right? Because if you're going BFT, if you're going looking at this level, but every node you don't scale because every node does the same thing. It reruns everything, and then eventually the longest chain wins. In Fluence, compute happens on that peer, and the other peers don't care, don't know. So as you add nodes or peers, you actually scale the network up. And we're also working on additional network management tools like subnetworks, for example, so you actually get the full efficiency effect of an infinity minus one scalable network, because this is where the centralized scaling solutions like Amazon, Google, Azure fail because they can't just hand this off to the network itself. They need to stay in control. They need to meter. They need to. It's theirs. And this is where, I mean, if you look back, I used to use Amazon a lot. 10 years ago, I'm absolutely convinced Amazon provided 5 nines, no problem. Today, I don't think they actually give you 4 nines. This is how bad their availability has become. And that's another, and one, in my opinion, one of the big bottlenecks is not that they're stupid, anything but they're smart, is the centralization and the centralized management of such a big network. It reaches its bounds, and this is why you want to decentralize, because if I'm over there and I'm using my IPFS and I'm doing my compute, I don't care what the rest of the network does, and I don't need to manage it. I just don't. And this is where I think these kind of models and the Fluence model really, really helps you on the compute side to scale up and do what you need to do, and you stay in your own subnetwork or condemn your neighborhood, and the network just keeps growing and executing. Then, so minor detour from Trust Graph. We have scheduled scripts. It's already working, but so we have these Aqua scripts, right? And there's no particular reason for them actually to be running on the client. So what you actually can do is you can deploy those scripts onto a peer and with some additional information, and basically a peer would run them just like a cron job. So you said you wanted executed every 13 seconds, which roughly coincides with a Ethereum block, right? Then every 13 seconds that Aqua script would be executed. And so not only have you not only do you have serverless with the network, you actually could be clientless in the sense that you dump it and you want to monitor your logs or whatever, but you dump it and it's just out there. I mean, it's not magic, but it's really cool. Yeah. Okay. Yeah. So you're basically asking me what's the SLA, right? Okay. Okay. Yeah. So this is something we're actually working on really, really hard. So right now, this is where trust graph comes in. So basically, so if let's say you have a mission critical, okay, let's say you have a script that is a trading bot that manages $100 million every time, right? I would strongly encourage you to run your own node, right? That if it's something that has okay, so with registry now we can do something. You can actually configure a cluster. So within that, so this would be an entire separate workshop. That's why I kind of didn't want to go there. But I no. I'm very happy to ask it. So because you will be able to do this like next week, where now you can configure almost like a round robin load balancing. I have 4 ones. If that one fails, try this, whatever. Now you just like with cron jobs, you always have this origin genesis problem, right? Who monitors the kickoff, right? So if you have a cron job today on an EC2 or a trigger on Amazon for your Lambda functions, well, you don't know, right, until you monitor. And now you need something else to monitor that script. So they could be smaller scripts that are distributed, and then you have to sort of make decisions on do I want to use a raft, for example, to start using leaders and monitor failure of the but that's up to you. And we as we move on, we're gonna keep pushing into that quote unquote middleware layer that enables more and unlocks more and more functionality. But at the end of the day, just like with blockchain, there's a recursive frustration. There's a rabbit hole where you monitor the monitor because it's not centralized. And for high value, the proposed solution from mine would be if you're running that much and you're making that much money, hopefully if you run this kind of big bots, you make a lot of money. Run your nodes, use registry, create a cluster, use a raft within that cluster, and basically make sure that everything is up or at least fails over as you would like it to be. Now, the cool thing is, if your trading bot is a good trading bot, chances are it's going to run on Ethereum, which means you have 13 seconds block time to actually figure shit out, which is actually kind of interesting because in other blockchains like Solana, you have half a second, so your ability to react is actually much smaller. So when you start now designing these now I'm like really veering off, but when you start designing these applications, you have to start thinking in peer-to-peer, right? And you have to start thinking in your environment, particularly if you're in Web3. And Web3, I mean, that big block time, I mean, without the big block time, most DeFi wouldn't even exist because all the flash loans are based on a 13-second block time. If the block time was only like half a second, your flash loans would only be half a second, and there's really not that much you could do in a half a second. But in 13 seconds, I can do a lot of things. So anyway, so as you design your systems, you should be aware of your context and then design, because if I have 13 seconds to manage failover, I manage it differently than if I only have half a second, right? And those are the kind of things you can think about and you can manage directly through the various tools we're giving you, so you actually can be cost effective in managing your needs relative to your environment, which is actually something a lot of cloud providers don't give you at that level, right? It's just there's your EC2 container or here's your Lambda and this is the trigger and off you go. Okay, now, in addition to the tooling, we have certain integrations already ready for you to use. The predominant one is IPFS. So just like it's a shame if you use IPFS and then you have to use Oz Lambda as your compute. It's just, I mean, it hurts my soul, right? It's the same if you use Fluence Compute. You don't want to use S3 or anything like that. You want to use IPFS, and you want to be in this decentralized domain. and really eliminate as many choke points as you can. There is still ingress and egress problems, just like in any systems control you encounter. But with peer to peer, you're in a pretty good environment. So basically, we wrote some adapters for around Fluence, around IPFS, and we actually went as far to run IPFS nodes as sidecars to Fluence nodes. So you have like it's super responsive, and one of the things we did. So if you go back to WebAssembly, one of the cool things about WASI is that it's sandbox, right? So it's totally insulated from the host, and you have a totally secure environment. However, since WebAssembly at this point, WASI doesn't have sockets, and a few other things. So WASI doesn't have sockets and persistence other than memory. We created a punch through the sandbox through permissioning that you can actually use binaries if the host wants you to on the host. So this is how you actually start using HTTP, for example, from your WebAssembly services to be basically you punch through and use the binary curl in this case for from the host node. And that actually makes WebAssembly or WASI services first-class citizens in terms of communication. I mean, you're not going to get WSSS or anything like that because the compute, just like Lambdas, it's not long-running in it by itself, right? Because if those services would be long-running and blocking, then your scripts would be blocking. And in that sense, it's not entirely different conceptually from how blockchains treat block sizes, because you can't have too much in it, otherwise it blocks the entire system. And so WebAssembly modules shouldn't be calling other WebAssembly modules directly. It should always go through Aqua. So you eliminate any kind of recurrent hangups. And WebAssembly modules shouldn't and actually can't call other WebAssembly module spawn other Aqua scripts, because first of all, you would have to have a lib P2P client as part of it, and then it would be hanging, and on a sudden you could bring mayhem to the entire network, which, given that it's open and permissionless, it wouldn't take long for somebody to try to do and succeed, actually. So we eliminate a lot of those problems by certain boundaries. We can do the same with Ceramic as we can do with IPFS, which is also really cool. I mean, Ceramic builds on top of IPSS and basically gives you a long-lasting address that overlays CIDs, which is really, really cool, because then you can sort of hard code that into a smart contract, for example. We have an example with an integration with Fluence and Near, and that actually what it does, it illustrates a really good use case for that Fluence Js, that JavaScript or actually TypeScript client peer that could be a long running node app to use for signing. You don't want to put your influence, everything is on the transport level is encrypted end to end, but the end is the host, not the service. So there's a gap between the decryption at the end and the service. So you don't want to send secrets basically across the network. We are working on there's a multitude of solutions we can work on, but the biggest one we keep encountering, particularly at hackathons, is of course how do I manage my private key? How do I sign for contracts? How do I sign my transactions? How to submit them? Well, in that Fluence and Near integration, there is an example of how to create quote unquote a signing node. It's a long running node app that manages your private keys, and then you can call the signing function from Aqua. So you manage your key, you never expose it. It's in your domain, and it's only the signing request, and then you can actually start using authentications and whatever filters to whether or not you want to sign it. And that, of course, extends to any EVM. We also have additional building blocks for you, particularly for the hackathon. So there's Fluence examples. So our GitHub repo is github.com/Fluence Labs/examples. And there are also a whole bunch of community examples that may not be necessarily fully up to date, but it shows you what has been done and what can be done. Various adapters and integrations. So even in Rust, and of course in Fluence JS, you can wrap entire libraries. So this is, I mean, this is an entire separate discussion at one point, what granularity you want for your function as a service, and it depends to a certain extent, right? I mean, and if you can wrap an entire library, you could actually split it up, or you could deploy it multiple times. Some of it just depends on the efficiency of the process and the cost, the gas to run it. And NFTs have been done, verifiable credentials, and decentralized identities, and a whole bunch of tooling. So if you're looking for help or inspiration for the hackathon, have a look at that. Okay. Code. I got a bunch of code I wanted to go through and show you. And anybody have any questions at this point? All right. So this was a very verbose, long introduction. So let me look where I am. Okay. So I created a repo. It's if you go into github.com, hang on, there's probably a way for me to put this into Discord, right? I put it in our in our Fluence network channel on Discord. And it's a very simple example. And apparently I haven't pushed the branch. Hang on one second. Okay. All right. Okay. Now we're in business. Sorry about that. Okay. So in that repo, there's a directory called Fluence Js demo, and then just a README. And you can use, for the hackathon purposes, you can use this Fluence Js demo as your template to get started. And basically, we have an Aqua file, and I just put a couple things in because I wanted to illustrate a few things. Basically, it's all about how to get a timestamp from a peer. Nothing really super fancy, but but there are different peers involved to get there, and because you have the client peer, obviously not interesting to get your own timestamp. You don't have to use Aqua for that. You just go your CLI and type date, right? But when you connect a network, that's the relay. That's your first stop, so you can get a time from that relay. And then I'm just gonna. So basically, this is what we're doing here. I don't know if this is yes. VM install doesn't work. Are you in? Hang on. Are you in the Fluence JS demo directory?
Oh, so yeah, I got Fluence Labs, Paris P2P, Fluence Workshop, and Hackathon, right?
Right.
Hold it down. Yeah, the only thing in there.
Okay, go into this directory. Okay, so you need to be in the Fluence JS. You need to be in the JavaScript template demo directory, and then if you, no, it's fine. And let's just make sure it runs. Oh no, oh yeah, I'm not in the directory either. So this is excellent. Okay, so when you're in it, it runs, and you're good to go. So okay, so npm start actually runs the thing. Okay, so we're basically executing, and I'll show you the TypeScript in a second. We're basically executing all these Aqua functions through the Fluence client, and we then just bring back our output to the client. Okay, so in Aqua, I have a bunch of functions in there for you to look at. So the first one is basically get the relay timestamp. And basically, what that says is it gives you as you connect from the relay, and init peer underscore init under peer underscore basically gets you the initiating peer without you having to specify it. So you don't. So within Aqua, you don't have to know what your peer ID is. It takes care of it for you. And then I said, well, this is kind of boring, just having a time. What we really want is like Hello World or Hello Paris P2P. We could change that. Hang on one second. And now we use the timestamp, and obviously I was too lazy to write or use a date conversion service, so I just said this is how many seconds have passed since the epoch, and we create this, and when we run it, it's somewhere up here. Oh no, hang on, I just changed it, so we need to do it again. Okay, here we go. And then in the next one, I said, hey, I'm not just interested in the timestamp on the relay. I'm actually interested in the timestamps from all my from my neighbors, my Kademlia neighbors. So one of the things you do in lib P2P is you actually have Kademlia neighborhoods, and that's it's basically your closest neighbors where the distance is the lookup time in the graph, the tree representation of the nodes. So it's not like a latency type measurement or whatever. It's just the lookup, which of course makes it very predictable in terms of how fast you can actually connect to your next peers. So basically, so now we're saying on my node, and here we input that node address. I want to say, hey, give me all my neighbors, and I do this by basically calling Kademlia neighborhoods of that peer, and I need to convert that peer to base 58. And then we have some optional parameters we don't care about right now. And then I get back a bunch of nodes. And usually Kademlia is, in Fluence it's 20. I know in Ethereum it's 27, but it's usually a smaller number. And so now we got these nodes, right? So we can call on each one of those nodes, either sequentially or in parallel. So I got fancy. I showed you a little bit of Aqua language conditionals. So we have if, we have try, we have catch. It's all available, and there's an entire Aqua book on that. But basically, so if we don't have any neighbors, which could happen if I run this on my local peer. I mean, I can run a Fluence node as a local peer. It's a single peer. There is no neighbors in the neighborhood. There's no Kademlia. It comes back 0. So I basically catch that here. And if I'm connected to the full network, then I basically say, hey, so if I have neighbors, start looking at it. And now in parallel, par at the end means execute this statement in parallel. We get timestamps from each one of those neighbors who wants to give us a timestamp. Now, it's a hot fix, but it has been the hot fix for a little bit of time. You have this statement operation dot noop, no op. It does nothing. It's right now it's a hot fix to get in parallel to get Aqua to make the topological changes, because every node is a different hop from where you start. So you're on this peer and you got all these peers from your neighborhood, and you want to execute the time, you want to get the time, you access each one of them. And there is a topological hop involved. And eventually this statement's going to go away, but right now you need it. So for hackathon, if things don't work the way you want when you parallelize, you probably forgot op.nlop. Okay. And then so this all executes in parallel. And the way we capture the responses in parallel is through a stream. So up here, I declared a stream variable. We know it's U64 for timestamps, right? And so we're writing the responses from those parallel calls into those timestamps. Now, for hackathon purposes, there are execution time limits. They're about 7,000 milliseconds right now. You can customize that, but if a peer doesn't respond within that time limit, you just move on. You don't block your script. You can if you want to, but you usually don't want to. You just move on, because the only thing deterministic in many respects for peer-to-peer network is that node unavailability is an expectation, not an exception. There's churn, nodes come, nodes go. And this is why, again, trust graph comes in, where it can manage reliable nodes with trust weights. And so now we join this, and I just join it on 5. It could be whatever number, length of nodes -1. And then I just return the timestamps and the nodes. And then the last function, basically, I wanted to show you, it's if I want to execute something on the initiating peer, I can use this statement on this node, on this initiating peer, do whatever. But if this is my node, I don't have to put it in. You should, but I don't have to put it in. So this is our Aqua script. This is our different functions. And now we compile it. And we compile it so it's consumable by TypeScript. So this is the output of the compilation from Aqua into Air, but with TypeScript wrappers around it. So this stuff in here, the XOR, SIG, blah, blah, this is your Air. This is actually the compiled Aqua. Everything around are wrappers in TypeScript that helps you with the registration and the easy reuse of those functions in a native manner, if you will, JavaScript native manner. And this is now what the actual index TypeScript looks like. So you import some support from the Fluence, which is the Fluence Js SDK. And Fluence is it's a super object. It's a very general, very capable object that lets you connect and deal with the connection. And then key pair, because everything requires key pairs. And then we import called Krasnodar. We have multiple network domains. It's one big network, but there are multiple domains within this. And the one we use for this purpose is called Krasnodar. There's 2 more. One is called testnet and one is called stage. And now we go to this compiled Aqua file, which we had here, which we just looked at. And we just get now these 3 functions, which we wrote in Aqua, which are now wrapped, ready for consumption in TypeScript to basically build these particles and push them out. And okay, so I got a few other things. So that just goes into the Async Main. So we basically create the connectivity, the connector to the network, which basically we specified the relay in this particular case up here. And we specified the secret key. We just specified it here. You obviously don't want, you're more than welcome to reuse that particular key in your hackathon project, but do not be surprised if competing teams mess with your services if that's the key you're actually using. So now we have a connection, and the connection is here, and then we can print out what our peer ID is and what relay we are connected on. So this is just your basic connectivity. And since it's not in the browser, it's actually a longer lasting node app type connection to the network. And you do this all by Fluence get status, and then you just append whatever attributes you're trying to pull. And as you can see, like, just like, VS Code, we have the markup for Fluence Js as well. So it gives you all the prompts you want. So now we get our first timestamp, which we call this get relay timestamp, which was, if you recall, this here. So basically what we're doing now is we're calling this directly, the Aqua directly that particular script directly from TypeScript. So TypeScript is now your interface into Aqua, and each one of those functions we compiled actually generated different air code. So every time we execute one of those functions, it's actually a separate trip. So you could actually string them together if you wanted to, and again within Aqua, call this, call that, call that. But for illustrative purposes, this should be you get the idea, right? And then we just basically keep calling each one of them, like I showed you before, and that's basically, I mean, that's all there to it. But this is sort of the most basic entry, particularly where you want a quick start, accelerate in your hackathon to get going. So you don't have to deal with Rust, which, even if it's easy, if you don't know it and you get 48 hours, stick with, if you know JavaScript, then obviously this is the choice. And then this is a very capable choice, by the way. So, okay. So that was one example. Now I want to show you something a little bit more complex. Okay. I told you about the IPFS integration. And I also told you that we can program the network to a certain extent with Aqua. So let me give you first the demo, then we go to the code. Okay, so what we're trying to demonstrate here is we want to use IPFS from Aqua to do something reasonably meaningful. And to demonstrate that when I told you we have an integration, we actually do have an integration. It's working today. So what can we do? So we develop a service, and let's just have a look at the service. It's in Rust. And here we go. And the service we want to do basically does nothing but calculates the size of a file as a service, right? It's not an inherent capability in Aqua to get the files. So you basically have this distributed standard library you can build yourself to do certain, or other people can do for you, and you can reuse to get this function as a service out there in a distributed, decentralized manner. So just a little bit on how you use Rust with or Marine with Rust to do it. So everything you mark up with Marine in Rust basically is an exposed interface. Everything that's not marked up, it's just compiled in the back. You don't see it. And so we basically create a result structure on an interface, depending on where you come from, language-wise it is, and then we actually create the way to compute the file. So where does the file come from in this particular case? And this is actually interesting. The way we integrated IPFS, we could just stream the IPFS file over HTTP, right? But that has problems, as we said, censorship resistance, all this undermines it, the choke point. So what we've done is we copy through the daemon, which still uses internet transport, but on the IPFS content addressability pattern. So the underlying IP addresses still could change, and you still get the address resolved, as long as it doesn't change faster than the replication of the address in the network is. And so you call on this file through Aqua. It goes through this adapter to IPFS. It gets it, and then it copies it onto the Fluence node. And then the WebAssembly service punches through the sandbox through permissioning to access to that dedicated file storage segment, and now loads up that file from that file path which we specified here, processes the file, and then whatever, gives you back the result. So that's the service we have. This is what we want to do. So now I created a service, and we again, like, you can clone this whole thing. We compiled it, and what the result of the compilation is basically the process files.waza. That's our module. This is what we're interested in. This is what we're deploying onto the network, and this is what we're calling from Aqua. Okay, so we have this IPF pre-integrated. We have now this WebAssembly module. So you could deploy this WebAssembly module from your machine, right? It's no big deal, but it's kind of inefficient. A, if you want to deploy it multiple times. B, if you want to use a different machine. So why not store it on IPFS, right? I mean, that's what IPFS is for. And you actually get a CID, which is unique to that particular WebAssembly file. So you actually can, not just at deployment through the blueprint, but pre-deployment, you actually can make sure that the WebAssembly module you want to deploy is the one you actually are deploying. So when you're a scatterbrain like myself, and I always have like 3 different projects, and I'm bad at merging my branches, then CID is the one thing that keeps me sane, because I can pretty much hardcode that, and then I actually don't shoot myself in the foot. Okay, so now I'm gonna get a little bit lazy. And hang on. Where is it? And I'm gonna use IPFS desktop to connect to the IPFS sidecar of that Fluence node. And the Fluence node we were looking at, so hang on, where was the, okay. So we connected, I selected one of it. It could be any relay you want, but I just picked one. We give you a choice of 3. It could be 10, it could be 1, it could be 1,000, however big the network, the number of relay nodes is. And we connected. So now we have a peer ID and a relay ID. And we also get, in this particular instance, the IPFS RPC address. So we can now use this IPFS address, and we copy and paste, which we're all really good at. And look at that. We are now connected to that single sidecar node on this Fluence, somewhere out in the Fluence network. So, that's kind of cool, but it's kind of, so whatever, right? So what we're doing now is, come on. We now do the second best thing after copy paste. We drag and drop. So we drag and drop this WebAssembly file onto the IPFS desktop, which actually makes sure it's going to end up on this IPFS node that sidecars. Okay. And we get our CID, right? Which is right here. So now we're back to the copy. So now we basically, in this interface, we now give it the CID, basically your content address, right? So now we have this on IPFS, and now we deploy that service onto the network. And all we do is we click deploy. So now we have the service deployed onto the network. On this particular node, you have your WebAssembly module running, and you can access it. So I don't trust myself, and I don't expect you to trust me one bit. Let's grab that cargo TOML file, drag it over here. Desktop says it's 139 KB. Let's see. Apple says it's a little bigger, but Apple says this is in bytes. They do it in metric. And we again get the CID, right? This is the unique content identifier for that particular file. So now if you look back at that service I just showed you, it took the file path. So we give it a CID, and now we want the size. Oh, look, it's exactly what we expected. And we actually could write that file size back onto IPFF if we wanted with a unique CID. So this is, and then of course, we are super nice people. We actually put in this interface to remove your service, and you can, and now the service is gone. But you could just redeploy it right from there if you wanted to. So there's obviously a ton of use cases in how to integrate store through, and you've seen how fast it is, right? If you have a decent network, which you would hope on the network. Not everybody has like, well, I'm from North America. I'm in Texas, so my internet kind of sucks. The big one. So this is like really fast for me. But you'd expect this kind of speed and low latency, no jitter on your basic network, right? Even if your client is not that well connected. So this is why things are putting it on IPFS is really cool, because you basically get sort of the full power of the network, including bandwidth, right? Okay, so how did we do it?
Not on the node. We downloaded the file on IPFS, put on the node, and then put to the site, right?
Yes. Now you could that you could attempt to bring the file onto, stream it onto a file saving service, for example, and then pick it up from that. But the whole, in this particular, the problem is, if you rely on the node for persistence, you are subject to the node's, guarantees, which may not be there. So this is why I said, combining P2P store with P2P compute is sort of a match made in heaven, because the node goes away, your files are still there. And the way we created that sidecar, as you've seen, like with semi-decent connection, is so efficient that you really, you couldn't do it you could, but you couldn't do it visibly faster than that. And it's always there, even if the node goes away. You just deploy your service somewhere else, you use the CID, and off you go. Okay. So how did they do it? This is actually now the really cool part of how did they do it, which is, let me go up here. So it's all in the Aqua. So if you remember, in the Rust file, we had all these structures, and which we exported. You can export them directly. You compile your file, and you can directly export your interfaces into an Aqua file. And now we want to process it. So now we have a little bit more code. But if you actually really look at what 78 lines of code do in a peer-to-peer network, if you really think about it, you could hardly redo that maybe in Python, but you certainly couldn't redo it in C, C++, in a regular environment, leave alone a peer-to-peer environment. Okay, so we want to deploy the service, right? This is sort of our entry in Aqua to basically take that file with that CID and deploy it onto a node, so it's callable by Aqua and executable. That's what that means. And as a result, you get this unique service ID. So if you look at function signature, we have the relay PID, which we got from connecting, right? Our client. You got the CID, which we got from the desktop. In this particular case, you could pre-calculate it on your own machine for that matter. It doesn't really matter. It's an input. You need you need to be able to get to the IPFS node, which we did with the multi-address, and then you basically have an error or a callback that just basically tells your Aqua script to tell the caller something happened or didn't happen. So we can, in this particular case, we can use that callback to update the React client while the Aqua script still keeps going. So we have the service ID, and now we basically, just like before, on relay, there's nothing else you have to do. You just basically say, on this relay, we want to execute IPFS get. So we wrap IPFS get with IPFS get, and basically give it the CID and the multi-address. And now in Aqua, this is the cool part. You do all this in Aqua, right? In Aqua, you now program execution from IPFS, just like it was a standard IO library, which is actually pretty friggin' cool. And then we assert that we actually got the CID we wanted to get. And then if we got it, we now create these module hashes. In our case, it was just one module. But from this, we create now a blueprint ID. So up here is this is how we add a module. So this literally adds the module onto the memory space of that peer for future execution on Marine. And then we create through those module hashes, which is we basically create the blueprint. So there's it's deterministic. So every time you follow that algorithm, you always get the same blueprint ID for the same set of configured module, always. And then we create this service ID. So a whole bunch of these functions we're calling are what we call built-ins. So we have a library called aqua-lib, which is, you can look at it as a standard library. And that basically allows you to eliminate tons of boilerplate with respect to creating things. And if you want, we can look at aqua-lib in a minute. But that's all given to you. So as far as I'm concerned, this is all you have to write, right? I mean, if I look at the efficiency in JavaScript or Rust or Python, I use this library. How much more do I have to do, right? I want to have no boilerplate, right? And I just want to be as effective and readable and clear as I can be. And again, this is in the peer-to-peer environment. As you can tell, I suffered a lot from writing low-level peer-to-peer applications. So I am like always in awe of Aqua because it's just so ergonomic. And then you get the deploy service, you get the service ID back, which we saw in the web client. So now we have this service, which is addressable, function addressable, and we can use it. And so now basically, if you use it to put file, again, on this peer, right, on this node, we want to now, the CID in this case is of the arbitrary file we want to calculate the file size for, right? And again, we get the multi-address, so we get it from IPFS, and we have the service ID, which we got from up here. So this was a little bit abstracted in the React client, but here you see it as clear as day. There's no magic in it. It's straightforward logic workflow programming. And then again, we have this callback function, right? Which in this case is a U32, which is actually your file size, right? That's what it reports back to the React client. And then, you know, if you have an error, you have a callback for error. Then we basically create our result stream or results variable, and we just do some aliasing here so we don't get our service IDs crossed. And then again, it's like, get this file we want to calculate the file size from, execute it on that particular peer. If we're successful, we calculate the size of that file where we now have the path. Again, the file was copied from IPFS to the node, access. So that's where the file path comes in. You're all nodding, so it's cool. And if the size calculation is successful, we now eventually write the result back. If not, we have a bunch of error reporting. And just a note, we saw par before. Par means parallel, and co is basically a coroutine. So writing back, since it's an I/O operation, you can keep continuing with the script in Aqua and have your coroutine do your callbacks without ever blocking your script, which is super important because the client, as I said, might be a browser, so the client might not even be there. So it just times out and goes away and doesn't block. And then at the end, this is how you get rid of a service. Like, I mean, obviously it's from the standard library, but basically just remove service ID, done. So you spend with all that, and there's a lot of white space, but there's some white space. We have 78 lines to write a peer-to-peer application that's utilizes peer-to-peer store and a minimal peer-to-peer compute function, fully decentralized. Anyway, so this is so for hackathon purposes, all these examples are available, obviously in our repo. And when you look at them, it's in many respects, it's so ergonomic. You can be so productive so quickly. It's truly amazing. And if you want to look at this, is not entirely the same thing, but it's close. Where we wrote this whole thing as the Node app without the React front. So that's also in the same directory. It's in the same repo. It's called Node.js instead of web. And basically, hang on, we can just run it real quick. So again, we connect to the relay. Where are we? We connect to the relay. Then we actually getting a file. We deploy our service. Then we get a file. It's arbitrary. It's some PNG file where we get from somewhere. And nice. This is super not good. It was just working before. Come on. Okay, I don't know, it hung up. Yeah. So it got hung up on the internet site where we download the JPEG we're using to calculate the file size from. Okay, and basically just before we connect, then we deploy the service, we upload that, and then here, just like before, it's the same artifact, it's the same WebAssembly one. Hang on, make it a little bit bigger, and get to the various addresses. Then we download a file, which is hard coded somewhere in there. Yeah, it's right here. So we download a PNG image, and we calculate the file size for it, and we get the file size back here. And you feel free to verify it yourself, and that's it. So it shows you not only again how you could run it as a straight Node app, as a CLI client, but actually also how all this works in the browser. Okay, any questions? Yeah. No. Okay. So they're different components. Let me hang on. This question is not the first time. So we have two core technology. One is called Aqua and one is called Marine. Marine is a WebAssembly runtime. And at this point, WebAssembly is written in Rust, and it compiles. So basically, you write your service, that file size service in Rust, right? And then you compile it to your WebAssembly, and then you just deploy it somewhere out there. And Aqua provides the programming language, the workflow composition engine, if you will, that allows you to string together, glue together, to compose multiple services into an application. And the reason you need Aqua for that is as there are multiple reasons. One is the way we use function addressability. You need to be able to resolve the peer service tuple into something meaningful, which you can do with your REST or JSON RPC. And then the other part is whether it's WebAssembly or not, in those computes, you need determinism. So you can't have parallelism with, I mean, even if you wanted to in WebAssembly, because the whole thing would croak, right? Because it would keep blocking. So what you do, I don't know if you know, for example, but a while ago, many years ago, actually decades ago, there was a clustering system OS called Beowulf. And Beowulf basically used desktops and small compute devices as an alternative to mainframes. So a lot of parallelization, what on a mainframe was part of your binary, now was taken out by Beowulf, the OS, and part of the controller, the control flow, instead of just one monolithic application. And Aqua basically does, in many respects, does the same thing. You wanna run 10 services in parallel, no problem. But the parallelization now is in Aqua. It's not in, what used to be your code blob. So it's, I mean, function as a service is the right but it could be a pretty fat function, right? It could be, I mean, it literally could be an entire library. But the point is that, so when you wrap things you have already, or when you want to rewrite them, granularity, those are sort of design principles you really want to look at to really make the system sing. But I mean, as I said, the system or what we have now allows you to be pretty productive. It's not, I mean, it's not production ready, but it's pretty damn stable for at every iteration. And I mean, we're still iterating really fast. I mean, we're a small startup, so we iterate fast, and sometimes stuff breaks. But we're pretty responsive. If you hit us up on Discord, even through the weekend, just do not hesitate, particularly through the hackathon. And we keep pushing forward. And I truly believe that for a lot of smaller projects, it's already just as capable as Amazon Lambda, just without the dashboards. But if you want to experiment with peer-to-peer applications and move small parts over to get a feel for it, how does the design change, how do I work in this ecosystem with IPFS or ceramic, it's ready, it's absolutely ready, it's good to go.